But why, some say, the moon?
11, 10, 9.
Why choose this as our goal?
Sequence start. The engines are on. 4, 3, 2, 1, 0. We have liftoff.
We choose to go to the moon.
It has a stark beauty all its own. It's like much of the high desert of the United States. It's different, but it's very pretty out here.
We choose to go to the moon.
Hello and welcome to another episode of NASA Science Live, an opportunity for you to interact with NASA experts and have your questions answered live. My name is Joy Ung and I'm your host for today's show as we talk about some very exciting news. The opening of one of the last pristine moon samples from the Apollo lunar missions. If you have questions, send them in using the hashtag AskNASA on social media or wherever you're watching this show today. When Apollo astronauts began bringing back samples from the moon to Earth over 50 years ago, NASA chose to keep some samples unopened and untouched. So why was that? Well, NASA knew that science and technology would evolve. So they wanted future scientists to be able to study these unique samples using new tools and state-of-the-art laboratories. This became known as the Apollo Next Generation Sample Analysis, or the ANSA initiative. And this past Monday and Tuesday, the very last pristine core sample of the moon from the Apollo 17 mission was extracted from its vacuum-sealed tube in one of the cleanest laboratory facilities at NASA's Johnson Space Center, which is the hub for extraterrestrial samples. This process was months in the making, and today we have some very special guests to tell us all about it. I'm joined today by Dr. Juliane Gross, Deputy Apollo Curator, and Dr. Jacob Bleacher, NASA's Chief Exploration Scientist, who can tell us how data from this sample will inform future scientists and missions to the moon. Thank you so much for joining us today.
Thank you so much for having us.
It's a pleasure to be here.
So, Juliane, you've been involved in this months-long process to open and extract this pristine sample from the moon. We're dying to know what that was like. Can you walk us through what these past few months have been like for you and your team?
Of course, I'm happy to do that. The process actually started about 3 years ago, and it involves a lot of planning and developing and testing, and really was a collaboration between all sorts of different institutions that includes NASA and the European Space Agency, the University of New Mexico, Washington University in St. Louis, just to name a few. And so the sample we're talking about is actually a very special sample. It is the lower part of a double drive tube that the astronauts hammered into the ground on the lunar surface and that then filled with rocks and soil. And the lower part of this drive tube was sealed into a vacuum container. And because it comes from deep within the lunar surface, and it's very, very cold there, any potential gases and volatiles that are trapped down there get sealed into this vacuum container and then get preserved there. And so once that sample came back to Earth, it was placed in another vacuum container just to keep safe. And really all, and I'm just saying all, that we had to do is just to, figure out how to actually get the gas out of that container before we open it, because we didn't want that to just escape. And so ESA developed a piercing tool for us, and then the University of Washington and St. Louis, they developed a gas extraction manifold for this particular purpose. And so all of this about 7 weeks ago, all the pieces came together, and they're now in our lab, and we tested them, and we were able to actually pierce the vacuum container and release all these gases that are trapped in there. And so you can see the manifold in the movie right here. And the gas gets then stored in these canisters that you saw a minute ago. And then we can take the gas from the canisters and distribute it to different scientists. And so here you can see the piercing tool in the foreground with us doing measurements and actually piercing the actual sample. And so the thing that we did after that was to CT scan the sample, X-ray computed tomography. CT scanning is what people usually know about. That's from medicine, when doctors scan you to look inside you without actually cutting you open. And we can do the same thing with rocks. And so you can see our CT facility here. And so that gave us the very first glimpse, looking through the vacuum container into the actual sample, what it looked like. And it was a really good thing that we did that, because it turns out the sample was overfilled, which is a great problem to have, but it made it really hard for us to extrude. So last week, Andrea Mosi and I spent all of that week to figure out a new way of how to open that sealed vacuum container and take the sample out carefully without losing any of this extra salt. And so just on Monday, or 3 days ago, is when we actually finally opened the sealed vacuum container and took the sample out for the very first time. You can see that here in the movie. That's the very first glimpse that we got. And so that is the first time anybody has seen the sample since it was sealed on the moon 50 years ago. And so for us to be the first people to actually do this was extremely exciting and fun to do. So yeah, it has been a long 7 weeks, but it's totally worth it.
Wow, that must be so exciting. And the process is just incredible. I bet most people at home thought you just twist a cap and open these tubes. I had no idea that there were so many different steps and that it was so involved. So Jake, these samples were collected on the moon nearly 50 years ago, and now NASA is planning to return to the lunar surface with the Artemis program. How will what we learn from this sample inform future human missions to the moon?
Yeah, Joy, it's a really good question. First, I just want to say how super exciting this is. I mean, that's really cool to see that video Juliana was just showing. I mean, that soil hasn't been seen by anybody for 50 years, which is so cool. And now we're going to learn about it. So, this is really an extension of our lunar exploration, right? We went with Apollo, and now we're going with Artemis, but we're going to a very different place. We're going to the South Pole of the moon. And in the South Pole, there are some locations, because the sun is coming at a very oblique angle to the very bottom of the moon, that South Pole of the moon. There are some depressions, impact craters from where debris from space has hit the moon in the past and made a depression. We never see sunlight down there. And so these permanently shadowed regions, we call them PSRs, permanently shadowed regions, never see sunlight. And so water that maybe was delivered to the moon by comets or potentially from within the moon itself, that gets into one of these traps is stuck there. We call these cold traps. And so some of the samples that we hope to collect now in this mission, in the Artemis program, would, we hope, have volatiles with them. And so what we're hoping to learn from this Apollo sample is how well did the container trap all of that material, those gases that Juliana talked about, any volatiles from the moon, and whether or not anything leaked into that sample from here on Earth. Because that's really going to help inform us how to do this well when we go to the South Pole of the moon. And just like here on Earth, any job that you might do, it's a little bit easier if you have the right tools. So we want to make sure that we get the best samples from the South Pole of the moon so that scientists can study it, so we can understand the water cycle and whether or not the water could be used as a resource for our astronauts. But to do that right, we really need to design that right kind of tool, the tools to pick up the samples and the tools to contain the samples, preserve them, make sure we don't kind of get them contaminated with any of our gases from here on Earth or inside of our spacecraft. So it's really exciting, not just to learn the science from this Apollo sample, but learn about the container that they put it into and how well it worked, how well it kept those gases in there. And you can almost kind of think about this as an Apollo sample, but it's almost like the first of the Artemis samples, right? We're just about to go, and here we are opening up a new rock for the moon. So it's really an exciting time for all of us.
Juliane, you've just opened this pristine moon rock sample. What's next for you and your team?
Okay, so there are a couple next steps. The first one we did on Tuesday is once the core gets pushed out of its tube, basically onto a table that has a mold so it can hold the core. And then we are scraping the very first millimeter off the surface very carefully, because that surface has been in contact with the core tube basically. And you can see me here in the video where I'm marking where we want to scrape the surface off. Yeah, here you can see it scraping. And we do this because we want to expose the pristine sample underneath that has never been in contact with any material basically from Earth. And so that cuts down on any potential contamination. Once that is done, so we finished that on Tuesday, at the very moment we have researchers from the University of Hawaii in our lab, and they're going to do hyperspectral analysis on the core as it sits in the cabinet at the moment. And that means they're shining light on it, and then they're looking at the light that gets reflected off the core surface, and they analyze that light. And that gives us some indication of chemistry and how the chemistry might change from top to bottom of the core. And that can also be used for ground truthing any orbiters that we have going around the moon who look at reflected light from the lunar surface, which is sunlight. And so once that is done, next week, Monday, is when we start the very tedious process of really dissecting the core. And that means we're taking it apart bit by bit, every half centimeter, we're taking a sample, and then we're storing that in little containers. And we're doing that to preserve any potential layers that we can't really see with our eyes, and that then can be allocated to scientists. While we're doing this, we're creating a preliminary examination, and that means we're describing what grain sizes we see, what colors we see. We will remove larger rock fragments, and then we will CT scan them again to see the inside and the textures. And then we're creating this big catalog where people from all over the world then can look at it, and it's specifically really useful for researchers because then they can select the best sample possible to do their best science possible. And so that's the next couple of months for us, really.
Well, that's really exciting. We have a lot of questions coming in online. If you have questions for our experts, send them in by commenting in the stream wherever you're watching, or by using the hashtag AskNASA on social media. So our first question is from Vegan in the Mirror on Reddit, and they ask, if you take a sample from the moon and close the container airtight, is it automatically vacuum sealed, or do you need to do something with it so it is vacuum sealed?
And that's a very good question. I can quickly give some insights, and then maybe Jake can follow up on it. So when you take a container on the moon, which is basically vacuum because the moon doesn't have an atmosphere, and you just close it, like as tight as you can, you just screw the lid on. That doesn't really mean that it's airtight, because there might be grains, from the lunar surface that get attached in between. There could be little cracks or in between. And so once you return that to Earth, our atmosphere, which is so much more pressure than the vacuum that you have in the container, it can seep into this container through all of these little cracks and nooks and like little gaps, basically. So in order to really vacuum seal it, you have to have kind of like a metal gasket or a metal ring that when you press down your lid, it really seals. It goes into all the little nooks and crannies and really seals your sample inside. And that's what the astronaut did with this vacuum container. There was a gasket or a ring that sealed it, a metal ring that is soft enough to really press into all of the little nooks and crannies to seal everything in there. Jake, do you want to follow up on that?
Yeah, everything that Juliane just described is exactly what we want to understand how well that worked, because we can update that somewhat as we move forward for Artemis, but it might be sufficient for what we need. And another part to that is understanding how we're going to be collecting samples in the South Pole. So we know how these samples were collected, and we know that this approach will yield a certain result, which Juliane and her team and scientists around the world are going to understand over the next several weeks. But we'll need to think about how that applies to where we will be sampling in the South Pole, because we're fairly certain there's water there. What we don't know so much is what the status of that water is. Is it a little bit of water mixed with lunar dust or regolith? Or is it bigger pieces of ice mixed in there? Or is it actually just solid ice? So there's a lot for us to learn. And so understanding really how well this process that Juliane and I just described worked for Apollo, how well it contained that over 50 years, that's very critical for us as we start designing these tools moving forward.
And so a lot of people online are asking versions of this question. What do moon rock samples smell like?
Well, I've never smelled a moon rock. That's a great question, actually.
Yeah, that is a good question. I mean, the astronauts always describe it as it smells like gunpowder a little bit. We don't really smell the samples. So all the samples that we have are bagged in Teflon bags in a nitrogen gas filled atmosphere, and that's where they get stored. And so we never ever take Apollo samples out and expose them to air, and sniff at them or anything like that. And so in this video here you can see us opening the core sample, but it is within a glove box, and that is filled with nitrogen gas, and it's very dry, so that the soil doesn't react with Earth atmosphere. So we're trying to keep the sample safe from any potential contamination. So you really can't take it out and smell at it. So I don't know the answer to that question.
But I think, Juliana, the point you made that smells like gunpowder is something that many of the Apollo astronauts commented on. So they actually put their suits on and took them off inside their habitat, basically like their living room, sort of. So they would put the suit on and go shuffle around and do the work. And as you know, from here on Earth, we go outside and you work outside, you get dirty, right? And so the astronauts, they had some of that lunar regolith on their suits. And in fact, you can still see that on the suits today. And so they did describe that smell as somewhat gunpowder-like. So, that's pretty much our best chance at knowing what lunar rocks smell like until maybe we go back and try that again. That's a really interesting question.
Yeah.
Lara de Mozak on Twitter asks, why did the Apollo 17 astronauts choose to sample from a landslide deposit? Did they also take a sample from flat terrain?
Jake, do you want to get a go with that?
Sure. They collected a number of samples. I don't know exactly how many, but they did collect a significant number of samples. So for any geologic problem that you're trying to tackle, you want to try to sample from several different locations so that you can understand processes that may be in effect across broader regions. So as a landslide, as noted here, you would want to collect from inside the landslide, adjacent to the landslide. There were several different geologic processes that the Apollo 17 astronauts were studying. They also identified some really unique aspects to the lunar surface. This is the mission in which they identified orange glass that's related to some volcanic processes. So the reason we want to send the astronauts there is because we can train them to think quickly. They see what is going on and they can make the best judgment call about what to pick up, what's the most important sample to pick up. And so in this case, they're trying to get into that debris kind of pile. If you think about a landslide, one thing that a landslide can do for you on the moon is bring you material from much farther away. We're a little bit constrained by how far, especially in Apollo, how far they could go. Apollo 17 had the lunar roving vehicle, which kind of looked like that dune buggy that they could drive around. And they actually covered the longest distances of any of the missions. Still, you look to things like impact craters or landslides to deliver material from farther away that you might not be able to get to. Another technique they used was to look up hills and see if any boulders had rolled down the hill. And they did that as well in that mission. They identified some places where rocks from a good distance away had come to them, so they were able to sample them. So you have to make those judgment calls about what you see around you and try to collect some sample of multiple different things that are going on as part of that history, that story that you're seeing in the rocks.
Another reason why they particularly also sampled this region with the core sample that we have is that the landslide deposit is very close to a fault, which is basically a gigantic crack, so to speak. And because they sampled so deep within the surface, one of the goals was to capture any potential gases. And the hope was that the fault line would be a conduit to like have the gases that are from within the moon that slowly degas outside of the moon basically deliver into this landslide deposit that then can be captured by this drive tube. And that was one of the reasons why it was sealed in a vacuum container to really capture those.
Doc Harry on Reddit asks, how do you account for what changes might have occurred due to time past compared to what they might have found if today's technology was available in the past?
Okay, so one of the reasons why NASA kept these samples safe for 50 years was that they knew that technology will evolve with time. And so the X-ray computed scanning, the XCT scanning that I talked about before, that's a technology that didn't really exist to that extent 50 years ago. And that gives us the chance to take rocks, like big rocks or drive tubes, just like we showed, and CT scan them, which is a method that we can use without hurting the samples. And so we can look inside the sample and we can see the minerals and we can see the texture. And so we can learn a lot about where the sample comes from within the moon maybe and how it formed without actually contaminating it or breaking it. Mass spectrometers have evolved over time. So now there's less samples that are needed and they get higher precision and higher quality data. And so again, that wasn't possible 50 years ago. And for the gas analysis, for example, that they knew that wasn't possible 50 years ago. And so now we have technology where we can take that little bit of gas that we extracted and actually get data points and learn about the origins of these gases.
Moose Cahoots on Reddit, they ask, are we still running projects with this sort of eye to the future? It seems shockingly altruistic to gather samples that won't be examined in the project runner's lifetimes.
Yeah, so the question, will we take a similar approach for Artemis? Is that what the question is?
Mm-hmm. Yeah.
Okay.
Like, will we? Yeah.
Real good question. So we certainly recognize the value in that now. Our NASA predecessors had tremendous foresight in their ability to think through. It's like, imagine at Christmas time trying to save a present, or at a birthday trying to save a present for a year later. I know I certainly couldn't get my children to do that, but it's we will certainly approach it in a similar way. We'll try with the amount of material that we're able to bring home on these missions, do the best job we can now. And I would say it's probably likely that we will also save some sample for future analysis. But there are also new techniques now that give us the capability of potentially doing some of the science without even opening the canisters. So as Juliana talked a little bit about, as techniques improve, it may be that we save some sample in containers, but we can still do some science without even opening them right now. So there's a number of different lines of thought on what we can do with this. I think that we will always have an eye towards preserving material for future analysis while trying to do as much as we can right now with what we have.
Conto Moore on Twitter asks, does the moon have a core?
Yes, the answer is yes. The moon has a core. It is debated how large it is or how small it is, but it does have a core. So the moon is a planetary body, and it went through a process that is called differentiation. And that really means just layering based on density. So when the moon formed, it was fully molten once upon a time. And then all the heavy elements, they sink towards the center, like iron and nickel, and that forms the core. And then all the very light elements, they're lighter than the melt. They rise towards the surface, and they make the crust. And then all the minerals that are somewhere in between, they build the mantle. So the moon has layers, a core, a mantle, and a crust. And if it was orbiting the sun by itself, and had a nice clear orbit, then it would be potentially considered a planet. And so that's why we call it a planetary body, because it has layers just like Earth.
And Speed of Light on Twitter asks, has there been any previous analysis of moon soil samples? And have you found anything surprising?
Yes. Sure. The Apollo missions have sampled the surface in cores, but also with rake samples or just scooping up soils. That was in Apollo 11, where they just took some samples just in case things didn't really work out well. And so those are a lot of soil samples. One of the big things that we learned from Apollo 11, looking at these soil samples, is that they found teeny white grains. They're called anorthosite grains. They're plagioclase grains. And so before Apollo 11, we really didn't understand how the moon formed. And with these grains, when they were discovered, the only way to explain their existence or their formation is that the moon at some point must have been fully molten. So gigantic magma ball in space. And the only way to do that is that you had to have a gigantic impact between two protoplanets that then made a lot of debris cloud. The inner part then formed Earth, and then the debris part that went around it coalesced to form the moon. And so if we hadn't looked at these soil samples, then, who knows what would have happened. But that sparked the idea of the giant impact and the magma ocean for the moon.
Wow, that's
amazing.
I think
another really important thing that we've learned from lunar regolith is that it's, might be refer to it as lunar dust, but it's very different from dust here on Earth because there's no water flowing and no atmospheric water around the moon. And so that dust, that lunar dust, is very sharp. It's almost like small pieces of glass. So every time, every little circle you see on the moon is a place where a rock has hit the moon, or something from space has hit the moon. So what happens is you get this process of kind of shocking and melting little batches of the lunar surface again, and then breaking them apart and shattering them. And that's what makes up that regolith, or that dust. And so learning that process has taught us a lot about how we're going to move forward with Artemis, because I mentioned earlier that the Apollo astronauts had a lot of dust on their suit. Well, you can imagine if dust was really irritating to your eyes and your lungs, which they did start to report on some of the later missions when they spent more time outside on extravehicular activities, or EVAs. We've learned that maybe we try to keep that dust out as much as we can. So that's really helping inform the way we move forward. And it tells us a lot about the processes that have affected what we see on the moon today.
Yeah, a really, really cool thing about lunar soil is that, as Jake said, because there's no water or wind or atmosphere that interacts with it, the lunar surface has been preserved since its formation, basically. And so you can think of it as a museum for planetary science. So everything that had happened over 4.5 billion years ago is recorded in that lunar soil. And so you can think of the lunar soil as being an archive that contains all the knowledge, the solar system climate, how the sun output might have changed over time, what materials have bombarded the surface that most likely also hit the Earth. And so all of that knowledge is stored in the lunar soil, and all we have to do is learn how to read this archive correctly, which is not easy.
So Taylor on Twitter asks, did NASA come up with a better way to collect moon rock samples for Artemis as compared to Apollo?
Yeah, so we have certainly learned a lot about how to collect samples, but we'll probably still use some of the tried and tested approaches that Apollo did. I mean, rakes are still really good at kind of sieving through the regolith, the lunar dust, to pick up small bits that could be used to, for instance, get the date of the rock, how old it is since the event that helped create that rock. We will probably still use hammers if we see bigger pieces of rock to try to break off a smaller piece. There are things like tongs that maybe help us pick something up that's kind of harder to get to or harder to reach. And we're certainly going to continue to use things like drive tubes, like the sample that we're talking about today from Apollo. I mean, these are all, fundamental techniques for how to collect samples. I think what we'll see is little changes to it. The head that picks up the sample might articulate slightly differently, or might not articulate if we found that it was difficult, or it got kind of caught up and gets dust in the gears or anything like that. So I think what you will see is kind of a refinement to the way we collect samples, until we get into some of these really dark places where we think we will find larger amounts of water. And really, we're going to have to learn what that environment is actually like. How cold is it? I mentioned earlier, we don't actually know what the makeup of the water is inside there. And there's probably other volatiles mixed in, some that aren't so good for us to maybe have around us or be exposed to. So we're going to have to learn a lot about that environment before we can probably determine exactly how we want to collect those kinds of samples. We also are going to have to learn, and this sample from Apollo will help us, how to contain them, but we also have to think about how to transport them. So if we want to get a piece of ice from the moon back here to our colleagues at the Johnson Space Center, we have to have a whole system that keeps it cold. And it might be that the first few we try to bring back don't stay cold enough. And just like the sample we're talking about, it may melt or vaporize into gas, and we would have that gas trapped inside the container because of what we're learning from Apollo. But ultimately, we'd really love to give the scientists a piece of, honest to goodness lunar ice, because that's what they tell us they really want to get to. So we got to learn how to do that. This is a whole process. This really is fundamental exploration in the truest sense. We're going to a place we've never been, and we're going to do things we've never done before. And so every bit of science and technology demonstration that we've done, starting with Apollo on to now, is critical in understanding how to do that. I mean, we really are standing on the shoulders of giants who started this process for us, and we're just continuing along that path.
So we have a question from Holly Hughes on YouTube, who asks, why do we need to bring a moon rock to Earth? What exactly do you hope to find?
I mean, I can take a first crack at that. We can also take instruments to the moon. Okay, so we've flown instruments on spacecraft. For instance, the Lunar Reconnaissance Orbiter has collected some of the images that you've shown while we were talking here. Other nations have sent spacecraft as well to collect data. We can take those instruments to the surface. Apollo took instruments as well to the surface. The problem is you can't take like the really best cutting edge type of thing, the thing that really makes the good detailed analysis. The reason we saved these samples until just now to open up, some of these measurements are done by instruments that are big. They're, sometimes, a whole room is where you put that instrument just to make a measurement of a tiny little piece of lunar material. And we can't take that, at least not now. So it's a combination. It's not really one or the other. We're going to go to the moon and make measurements. We'll make observations. And we'll collect material to bring back to put into those better instruments here on Earth so we can really dig down in there and get the real detailed information that we want to look for.
Well, Jake, Juliana, we've got more questions for you later on in the show. But first, let's hear from a very special guest who knows a thing or two about how these samples were collected, because he was there.
One of the most important tools that we had was this core tube, double drive tube, and you could drive these into the surface. Now, it's still very difficult. It was the best we had, and we got quite a number of very good cores that are giving us new information. It was anticipated early on in the Apollo program that analytical technology would mature, would become much more sophisticated with time, that we could gain new information from the same old samples. And it makes it very, very exciting for everybody. In fact, Apollo never ended for lunar scientists.
I'm now joined by Andrea Mosey, Apollo processor, who has worked in the Moon Sample Lab for 46 years. Andrea is part of the team responsible for this historic sample opening. Thank you so much for being with us here today.
Thanks for inviting me. It's my pleasure.
So Andrea, you were in the room where it happened. Can you tell us what that was like?
It was very exciting. The entire process of removing the sample from the core cabinet, assisting with the gas analysis team, then moving the sample over in the core cabinet for opening it up and the extrusion. It was historical. It was very exciting. This is the first time that anyone got to see the sample, and we were the first ones to lay eyes upon it. Yes, that was amazing.
And you've seen many lunar samples opened. How was this one different for you?
The samples we processed daily were returned by the astronauts in rock boxes and bags. Those samples were then weighed, packaged, bagged, and stored in our pristine sample vault. They remain there until scientists, researchers request them for allocations. The samples that we're opening now, the core samples, have never been opened, never seen, never researched by anyone. So for them to be opened now, and we were the first to open the container and the first to see the samples, that was awesome.
That is so exciting. Andrea, thank you so much for being with us, and huge congratulations on a successful lunar sample opening. Best of luck over the coming months.
Thank you so much.
Now, don't go anywhere. We'll be back to answer more of your questions. But first, let's take a look at what this Lunar Sample Lab is really like.
For over 50 years, NASA astronauts and scientists have explored the universe, searching for ways to study the elements and materials that make up the solar system. In NASA's early days, the Apollo astronauts walked the lunar surface to collect moon rocks and soil for study back on Earth. In all, Apollo explorers sampled 842 pounds of lunar material. Today, those precious samples are curated within NASA's Astromaterials Research and Exploration Science Division, or ARES. Many of those lunar samples are stored in their Lunar Sample Laboratory facility at NASA's Johnson Space Center in Houston, Texas. NASA curators work to preserve the samples for ongoing and future scientific research. The samples are protected in secure and environmentally controlled vaults. Each sample is sorted by mission and stored in Teflon-based bags that are kept in cabinets filled with nitrogen gas. To this day, scientists from around the world study and analyze the samples to answer important questions about the moon's formation and history. To preserve their integrity, NASA curators follow strict safety and handling processes when working with samples. It begins with a laminar airflow change room. This minute-long air shower keeps the labs where they work pristinely clean. ARES scientists must also wear special gear, including a whole-body, non-particle shedding polyester bunny suit and triple-layered gloves. They also use custom tools to protect the samples. Moon rocks may only be touched with Teflon, aluminum, or stainless steel tools, and the dry nitrogen atmosphere around them. This allows curators to carefully examine samples while maintaining their original condition. This process ensures the samples are not contaminated or destroyed and can be used to produce scientifically accurate results. Technological advancements, including next-generation microscopes and other devices, allow researchers to examine the samples through new methods, resulting in important discoveries that answer some of our oldest questions.
We have a lot of questions coming in online. If you have questions for our experts, send them in by commenting in the stream wherever you're watching or by using the hashtag AskNASA on social media. So let's dig in. Baseboy Logos on YouTube asks, are there plans to bring back more lunar samples with the Starship Human Landing System or Artemis programs?
Well, the Artemis program absolutely has objectives associated with bringing back samples. And the way that we're doing the missions now is working with our commercial partners to build many of the key elements. So the SpaceX Starship that was referred to in the question is one of the parts of the pathway that's going to get us to the surface for Artemis 3. So it's going to be able to transport our astronauts from a lunar orbit where our Space Launch System and Orion spacecraft will deliver the astronauts. So they'll go into a lunar orbit, and then they'll get on board with the SpaceX lander. And then they'll go to the surface, they'll do their work, and then that will bring them back up to lunar orbit. So it's a critical piece of the pathway. And I mentioned earlier how we have these samples are going to go through a pathway to get them back here to Earth. And so each part of that pathway is critical. And every part of it is working with a different partner out there in our commercial community. So it really is an exciting time to be thinking about sending our astronauts there, bringing them home with rocks from the moon. I mean, it's a really cool process, and we're really looking forward to all the collaboration we have with so many different partners.
Rezius on Twitter asks, why were the samples sealed for 50 years?
Okay, so the samples were sealed because NASA had the good foresight. They knew that technology will evolve with time. They knew that we will come up with more questions that we didn't even know how to ask or why to ask in the past. And so the more we learn about the moon and the moon-Earth formation, since they have a shared formation history, the more questions we can ask, and the more technology gets evolved, the more detailed of questions we can ask to really, extract the information that are stored in these samples. And NASA knew that 50 years ago, and so that's why they kept a subset of samples sealed and safe, so that future generations of lunar scientists get a chance to look at samples that haven't been opened before and that haven't been contaminated to any degree. And so that was really great. And yeah.
Arthur on Twitter asks, what is it like to touch a moon rock?
That's a really great question. So we don't really touch the moon rocks when we work with them because our hands are gloved. So in the movies you have seen that we're wearing these bunny suits, right? And then we have gloves on, and then you work with the samples inside a glove box. So you're sticking your hands inside these big black gloves that you see here in the movie right now. And so when you handle these samples, you can't really feel them. You can, and the samples are back themselves, in Teflon themselves. And so you can maybe feel the weight and how heavy it is, but you can't, really touch them with your bare hands because we don't want to contaminate the samples. Our hands are dirty no matter how well you wash them. There are always particles and organics on it. And so we don't want to contaminate the samples with any of that because researchers might actually look at potential, organic building blocks that might have been existed on the lunar surface. And so we really try very hard to keep the samples as protected from us as possible. And that's why nobody, grabs them and take them out of the cabinet and holds in their hand. That's just not what we do.
Jordan on Twitter asks, how many lunar samples does NASA hope to collect with the Artemis missions?
Well, we think about it more in a sense of how much mass we can bring back. Because you have to remember, we're launching off of the surface of the moon with rockets. And depending on how that vehicle is designed, it can carry a certain amount of mass. And in fact, that's why we are trying to work with multiple different partners, because we want to see what kind of creative solutions they have to launching mass off the surface. So the objectives that we have on any given mission.
Yeah, all the samples are also very different. So if you think about it, the astronauts can pick up big chunks of rocks, or they can take core samples that, just like we talked about, today here. They can take scrapes of the surface. And so it really is driven by what kind of science question you want to answer, and that will also drive what type of samples to collect. And then as Jake explained, how much mass you want for those samples. And so there's a lot of discussion going on between all sorts of different groups and scientists and engineers, and yeah. Hopefully we'll bring back lots.
Yes.
I think we all agree on that.
Adesh on Twitter asks, doesn't the oxygen and nitrogen in our atmosphere react with the samples when they're opened from the vacuum container?
That's a very good question. And the answer is yes. If we would take the vacuum container and just pop the lid open here, it would totally interact and react. And there's also water in our atmosphere, so that would interact. And that's why we don't do that. We have these special cabinets in the Apollo lab, and they're filled with nitrogen atmosphere. So it's just nitrogen, which is inert, so it doesn't like to react with anything. And so that's why we open the vacuum sealed containers in there so that it cannot react with anything and it stays as pristine as possible. Yeah, you can see me brushing off some of the excess soil away there. And so that's the very, very first picture that was ever taken from this particular core once we had it open. That was on Monday this week. So
Max on YouTube asks, was this sample soil? Is it like soil on Earth? And did it contain rocks or any other organic matter?
That's a very good question. So part of the ANGSA program is to look at the soil. And we call it soil, which I guess is not quite correct. On Earth, soil, the word soil is meant for dirt that has organic material in it. We don't really have that on the moon. The correct term would be regolith, which is like the finely pulverized layer of the lunar surface, basically. And within the ANGSA team, there are people that look at the organic compounds or organic building blocks, so to speak, and whether they can detect any in this lunar soil. That's very, very hard to do because the moon doesn't have an atmosphere, and so the solar radiation is basically sterilizing everything. And there's always the chance of that we are contaminating the sample potentially, even if we try to have it in a very pristine environment with nitrogen atmosphere. And so this particular study from ANGSA is very important for these researchers to look at what they can find. And so when we're sending them samples from this particular core, we're also sending them something that's called a witness foil. And so when we open the sample, we are also opening a baked out aluminum foil that sits in the cabinet that could collect any potential contamination that comes from Earth, basically. And so then they can compare the organics that they find on the foil to the organic compounds they find in the lunar soil, and then really understand whether what they're seeing is actually from the moon or what they're seeing is from Earth that got in the cabinet somehow.
Debbie Schultz on Facebook asks, has any of the moon dust been exposed to Earth's atmosphere? And if so, does it change?
I'm sorry, I kind of broke up there. Can you say the question again?
Yeah, of course. Has any of the moon dust been exposed to Earth's atmosphere? And if so, does it change?
So when researchers and scientists request lunar samples, sometimes they want to do measurements in which they have to open the sample and put it inside an instrument, for example. So when we allocate them the samples, we put them in containers and we seal them in a Teflon wax, we send them out. But then in their labs, they will actually open the Teflon bags, the nitrogen atmosphere escapes, and then they will open the little containers and pour the soil out onto a surface that then they can analyze it. And so, yes, soil definitely has been exposed through research to Earth atmosphere. And I don't know how that would change the soil. Over time, if you have it exposed long-term in Earth atmosphere, it could maybe change slightly just because we have water in our atmosphere. And so that can interact with iron and maybe form a little bit of rust. But I don't think that it changes a lot over time in general.
And so the last question I have for you is one of my own. What advice would you give to someone aspiring to get involved with NASA's sample curation program or the Artemis missions?
I'm going to let Jake answer that first, and then I'll jump in.
Okay, I'll take it first. I'll go first. Yeah, that's a wonderful question. I love this question. The way I like to answer this question is, first of all, figure out what you like to do. What really motivates you to get out of bed in the morning? What are you excited about when you wake up? Because I can almost guarantee you, whatever that is, NASA has people that do that. So think about that. Try not necessarily to be exactly what you think NASA needs today. It's more about what NASA's going to need to do in the future. Just like this Apollo 50, or this sample from 50 years ago from Apollo is a great example. If we had only ever tried to build instruments the way they were back then, we wouldn't have even needed to preserve a sample this long. But it's all the creativity, everything we've learned in 50 years that has put us in a position to do this. All the engineers, all the scientists, all the folks who think about that, they're the ones who really enabled us to do what we're doing now. Artemis is just this exciting, complicated solution to a really difficult problem, going to the South Pole of the moon to collect samples, make observations. I can all but guarantee you that we need such a diverse group of folks to work on these problems. So, that said, understanding math, science, and engineering, those are really key things here. But we're going to have to work with partners. So, understanding how to talk to our international partners. So, overcoming language barriers, we need help communicating. There's just so many different ways that you could end up working for NASA. It's really hard to say one. I'm a geologist. I studied geology for my whole way through school. I got a PhD. And then, now I work in a community that's almost all engineers. So now my job is to communicate with people like Juliana who still do the science all the time. And, so you never know where your path is going to lead. So find something you really like and start learning how that fits into or maybe solves a problem down the road for us, because that's what we really need.
Yeah. My answer is pretty similar to what Jake just said. If you figure out what you're really passionate about, and that can then be your driving force, and because you're passionate and excited about it, that automatically means that you're also going to be good at it, because that's what you want to do, right? And so once you figure that out, there are so many ways to get involved also with curation and processing these samples. I also have a geology background, but my geology background started with Earth. And so I studied Earth, and then when I got a PhD after that, that was still Earth related, I switched fields and then became a planetary scientist afterwards. And so, if you go to school and even to university and you're not exactly sure where you fit or what you want to do, just because you started out in one field doesn't mean that you cannot end up in a different field, And so there are so many opportunities, and that, ranges from geologists to engineers to medical people. We need to understand what the dust really does to the human bodies once the astronauts are on the surface. Artists and outreach people, everybody's really important for these missions. And because Artemis is a plan to actually stay on the lunar surface, there's so many years to come. And I get so excited about it when I think about our kids, right? Like, they will grow up with Artemis and they get to maybe even go to the moon and look at these samples that are being brought back. And so that's all really, really exciting. And so just, keep pushing and you'll get there.
Well, that is all we have time for today. Juliana, Jake, thank you so much for joining us and answering so many questions from everyone online.
You're very welcome. This was a lot of fun.
Yeah, I'm glad people have so many questions. This is what it's all about.
And thank you to everyone online for participating in today's episode. To stay updated on all the science planned for the moon, follow NASA Moon on Facebook and Twitter. You can also visit nasa.gov/moon for the latest news. NASA plans to send science, technology, and humans to the moon with the Artemis program. And the first launch of the rocket that will send humans to the moon happens this year. And so for updates, follow NASA Artemis on Facebook and Twitter. Thank you, and see you next time.
I have a feather, in my right hand a hammer. And I guess one of the reasons we got